Okay, hello. So, where we left off last time was this two-phase commit, right? The transaction model. So that's where we're going to go to now. So, the basic structure of two-phase commit, you have some transaction coordinator that says, there's this transaction that's going to happen, and it's going to involve a bunch of related databases. All of those databases are governed by software agents called resource managers. So, when a transaction comes in, turn off that. There we go. When a transaction request comes in, the transaction coordinator tells all the resource managers, here's a transaction we're going to do, get ready to do your part of it. And each individual resource manager will pencil in the changes to its database, right, and cascade those changes to all the databases that it's supervising, and it's going to prepare rollback records so that if something goes wrong, it can recover. One at a time, each of those resource managers notifies the transaction coordinator that we're ready to go. We've penciled in the changes and we have our rollbacks in place. When the transaction coordinator has heard back from all of the resource managers, that's the end of the prepare phase. At that point, the transaction coordinator knows that either A, the transaction can go through, or B, if it fails, the system can recover. So at that point, the transaction coordinator tells all the resource managers to commit to the transaction, right? Basically make the database changes permanent. And one at a time, all of the resource managers do that. And when they're done, they tell the transaction coordinator. So every resource manager says, okay, I've done it, I've made the changes permanent, send it in. When the transaction coordinator has heard that all of the resource managers have made the changes final, then it knows the transaction is done. That's the end of the commit phase. So at that point, eventually, the system is fully updated, all the databases are in line with each other, and the transaction coordinator can eventually get rid of those rollback records, right? So it can say, okay, the transaction's done, you don't need to hold those rollback records anymore because, the transaction has been completed by everyone. And the end goal, you have one transaction that involves multiple related databases. For example, somebody buying something means a credit card deduction happens, Amazon gets some money, inventory gets updated, supply chain management gets updated, all of its data systems for item popularity get updated. At the end, all of those are pointing in the same direction. They're all showing that either the transaction went through or that it didn't get through. Either way, all those databases are consistent with each other. Okay? That's the point of two-phase commit. And there's a text write-up here and another link to a similar Oracle thing to what I showed last time, but that's all that is. Okay, so in case you missed two-phase commit last time, I did a quick recap for you. All right, a couple slides on transaction security, then we'll talk some stuff about network architecture, then we'll talk a little bit about object description languages, and it's all kind of blended together. It's all one big bubble that fits well in a single lecture. So, transactions have information that you don't necessarily want to get out, right? So credit card data, you don't want people to grab your credit card number and security code, what items you've ordered and when they're going to be delivered and where they're going to be delivered. For example, if I am ordering something expensive from Amazon, like, diamond jewelry or something, I don't want the various thieving motherfuckers in my neighborhood to know exactly when and where it's going to get there, right? Package theft is a real thing, okay? And anything the customer would prefer remains private, right? So if for whatever reason you got some stuff you don't want the rest of the world to know about, you don't want that getting out. So systems need security to avoid all these costs, right? Costs of lost goods. For example, if the credit card gets stolen, right, the info gets stolen, you're not generally much on the hook for that. The cap is usually $50 or so, but the credit card company could be out a lot of money. Lost customer loyalty, right? If people find out that their transactions are becoming public and they don't want them to, they're not going to come back. And of course, legal actions. Depending on how negligent the company is in safeguarding security, they could potentially be held liable. So, transaction security is very important. The flip side of that is fraud detection, right? So, fraud detection, Amazon wants to make sure that all the transactions coming in are basically for who they're purported to be for. And the baseline technique, you have some historical data that you assume is pretty good, and you compare things to it and see how far different they are. That's the basic technique of security. You look at data that you know is okay, and then you say, okay, and we have this other batch of data, how is this different, right? So, for example, one of the things a network might do is say, usually we don't have much traffic between these 2 points on our network. Now we have a lot of traffic on there. That's unusual. Let's check that out. Let's look at the individual packets that are traveling over that part of the network. And they like scan in on them and see, these packets are funny. They say they're for one application, but they're structured in a very different way from the data that application usually gets, right? So for example, you could be sending a video, which would typically be a long stream of packets, but instead, right, it's some kind of malware thing and it's sending short strings of packets, or the encryption is a different format from what it typically uses. All those kind of things are things that security tools detect. So the same kind of thing with fraud detection. Amazon's going to look at each particular data event, right, a particular purchase, and see if that lines up with all the data that Amazon has about purchases and about you in particular. Now in this case, Amazon has a very big advantage because it has a long window of historical data about customers, right? So I know I bought my first thing from Amazon at least 20 years ago, so they have like that. My wife is the big shopper in the family, but I have, some historical data there, and they obviously have a lot about her. And that's difficult for companies to replicate, right? If you're some company, this is your first year operating, you're simply not going to be able to have that kind of strong data for fraud detection. So, a couple different ways they could do it. Number one, looking at particular customers. So if they say, this purchase is nothing like the sort of things you usually buy. For example, if I were a jewelry person, and maybe it's a routine thing for me to buy expensive jewelry every month, right? I could be like Mr. T and want my collection of gold chains, whatever. It might not be out of line if I buy a box of gold chains. However, right, in my particular case, you can look at me and say, hey, he's probably not the kind of guy who buys a lot of jewelry. And you'd be right. When I bought my wife's engagement ring many years ago, I instantly got my credit card held, right? They said, this is not the sort of thing that this guy buys, right? So, yeah, they instantly put a hold on that, right? Purchase type, right? Expensive jewelry, volume 1, which is more than 0, and the price, price was by far the most expensive thing I'd ever bought in my life to that point. So, other things, they might look at the delivery address, right? So if your delivery address is in a foreign country, for example, and you have no prior relationship with that country as far as Amazon knows, they're going to think, that's a little sketchy. Maybe somebody overseas got your card number and they're having stuff shipped to them. So that could trigger it. Other things, certain products are inherently more likely to be used for fraud. For example, big two, jewelry and electronics, right? They're expensive, they're compact, they're easy to fence, right? If you steal them, you can sell them off to somebody and get a decent amount of money. Versus stuff like books, right? Nobody's gonna, it would be very unusual for somebody to buy like 20 books and then try to resell them because that's, a fraudulent transaction. It really wouldn't be worth the trouble. At that point, you might as well get a job. The same thing for like kids' toys, right? Nobody's gonna buy a Croco-Glock and then try to, sell it to what? To Goodwill for 50 cents or something. Doesn't happen, okay? But unusual delivery volume is another thing. So we always used to buy diapers for our kids. We get a box shipped out every week. One box of diapers, that's not going to throw off their system, right? But suppose I had 100 boxes of diapers delivered. They might say, hey, we don't know about this. This is not the sort of thing you usually buy. It might demand some extra scrutiny, okay? So, looking at individual customers and the stuff they've bought, or looking at the products that are known to be more typical of fraud. Okay, and Amazon, again, Amazon has a lot of data. They can have a pretty good process about guessing what's right and what's wrong. And of course, the credit card companies do this as well. It's not all inside Amazon. Okay. Now, network architecture models. So, the basic thing with network architecture models, we know a couple things. The user is going to have an interface, right? You got your device, it's got a screen. On the screen, there's some kind of application. You're doing what you're doing with the system. The business, for sure, we know the business has the data, because if you had the data, you wouldn't need a network, okay? So those are the two things we know. The other details, the application and how the application tasks are distributed, right? Whether the business is doing a lot of them for you, or whether you're doing a lot on your own machine, that's flexible, okay? So, two big architecture styles. One is client-server. Client-server is kind of old-timey. It peaked in the 80s, and in the 90s it was starting to go away, at least for the big players. And Ntier. Ntier is the big one that all the really large-scale systems are using these days. Actually, it started off as a 3-tier architecture, but then people started adding in new features, and so it was N implying there could be more than 3. So, the first one we'll talk about, client-server. So I'm going to lift this document here, this picture, and put it in Paint. Okay, because paint is our friend. There we go, boom. So, what we know about client server, there's a server machine and there are a bunch of individual clients, okay? The server machine primarily runs the apps and stores the data. Now, of course, some of that could be distributed to the client machines, right? So the client machines typically run the interface, okay? But most heavy computations happen on the server, okay? So we're assuming that we have thin clients, not thick clients, okay? At least the really heavy computations, those are happening on a server. And this is typical of things like Facebook, for example. Not client server in particular, but the idea that your client machine, it's running a browser, but all the heavy duty processing, that's going on internally to Facebook. Okay, because they have all the data right there. If you run a search on Facebook to try to find one of your friends, you're not going to download the whole Facebook pile of data and crunch it on your mobile phone and find it that way, right? Facebook's going to do that work for you. Okay, so client-server architecture, the basic problem is this. Works fine if all the apps and data for a work group or department can be kept on one machine. Okay? And back in the 80s, that was not an unreasonable setup. There was data, but there wasn't crazy big amounts of data like we have now. Okay, so you'd have a work center, right, some floor of a building, whatever. They'd all connect to one server, and they'd all be running their applications on it. And it worked fine for that. But the problem arises when the data is on multiple machines. Okay? When the data is on multiple machines, if you want to get to it, you have to switch over to that other machine. And that entails basically making a new connection. And many of these connections, right, they're wired in. So there's actually like a switch port, and you plug into that switch, and you have to use something to connect to another device. It's kind of a hassle to switch machines, right? Even if you've automated that, it's still going to take some time because you have to authenticate who you are to the server to prove that you're able to access that data. It's kind of a hassle. So when the data is on multiple machines, you need to directly connect to another one, okay? And that's a hassle. Other problem, clients have direct access to the databases, okay? This is a problem because it entails a security risk. So you guys have probably heard of the iCloud hacks, yeah? So the iCloud hacks, a lot of what happens is you have famous people sending naked pictures of themselves to their significant others, I presume. And then some hacker comes along and is somehow able to access data that's not in his account, but it's on the same machine. And they download all that and they check it for images, and the images, oh yeah, this is so-and-so, let's post that on the internet, okay? That happens. That's one of the problems that can happen when other people have, access to something. So you want to be very careful, very cautious about letting, clients directly connect to a database. And in particular, for something like Facebook, you really don't want to do that because people's data could be scattered all over Facebook, right? All the different things, what your friends are doing, what you're doing, many different machines, right? It's not just glommed into one place for your account. It's stored all over. You have to give people wide latitude to directly connect to a whole bunch of databases. Facebook doesn't want to do that. It's a security problem. Okay. Which is a security risk anyway. Okay. So that's the thing. That's with client server. It works fine if, it's an internal operation and everything you need can be put on one machine and you don't have to switch around. Then it's all right. And again, in the 80s, that was generally the case. Nowadays, not so much. Okay. Excuse me. So, client server is this basic model where the clients, in this case customers, they directly obtain data that's on the servers, and the application logic could be on the clients, in which case it's a thick model, or it could be on the servers, in which case it's a thin model, right? Thin model is basically other machines do the work, and you get the results through the network. So, problems, the security issues, and it's difficult to scale, right? If you get a lot more data, you have to replicate it to a lot of different machines, and you have to control clients accessing those machines. Okay. Now, if it's small scale, it's fine. It actually really is. It's cheap to build and deploy. There's not a lot of headaches to build in, right? You just connect devices directly to the server. Your data is all stored in one place. That can be handy and convenient. There's only one place where you have to do patches and upgrades. Okay, so there's just one machine. You just do the one server. And it's easier to monitor security in the sense that you're just looking at one machine. Okay, and that, again, the patches, you do that. You get the patch, you install it, boom, you're done. Okay? Problems, it's difficult to expand or modify, right? There's performance issues in the sense that if you're a thin client model, then as you add more users, your system's gonna slow down, right? So at some point, if you have too many users attached to one server machine, you're gonna have to make a duplicate of that server machine somewhere. The other problem, if you have a thick client model where most of the application work happens on the clients, then the application patching is probably gonna have to be left to the users too, which creates, the usual security headaches. And there's a single point of failure, right? If that server goes down, you don't have any backup in place to switch people over to immediately. I mean, yeah, you could set up a backup in place, but still, switching over to a new machine is still going to be a hassle. It's going to be slow. So, if you're going to have this kind of model, and they do exist in some places, if you're going to have it, you definitely want to keep it internal to your organization and away from the internet, right? It's typically used for very secure internal operations where you don't have this, these kind of problems don't arise. Okay, the other one, Ntier architecture. So, Ntier architecture tries to solve the problems of client-server architecture by adding intermediate layers. So, we'll talk about this. So, for example, okay, we're going to do this, and then we're going to make some copies, and then one more. So I'm going to do some dots here. The dots here indicate there are potentially many more things. Okay. And we'll mark these data in just a second. These over here, up above, they're data. Down here, many clients. Okay. So data, apps, clients. So again, the client machines, that's us. That's ordinary system users. The apps, those are application servers. Okay, so application servers data, those are machines holding the databases, right? So think basically hard drives. Okay, now what's the advantage here? Well, number one, if a client wants to access something, they have to go through a separate layer to get to it. Okay, so advantages of Ntier. Number one, clients don't directly interact with the data tier. Okay? Instead, they go through an application server. And the nice thing about that, it adds an extra layer of protection, basically. So if you're just accessing data, you can form some oddball query that could potentially reach beyond the confines of where your data is supposed to be. But if you're going through the separate application server, basically you have to formulate your query in a standard way that the application is going to recognize as, oh, this is actually not an unusual query, this one is actually okay. So you can put extra layers of protection in there. It's better for security because you're not directly interacting with the data machines. Another thing, if somebody tries to do a denial of service attack, right, for example, they try to overload this system with connection attempts, if they're connecting directly to the database, that's really hard to stop. But if they're not, if they're going through, oh, I've connected to this application server, you know what? Facebook or Amazon, they can just shut that server down. They can shut that server down, say people are overloading this one, but they can shut it down quick and it's not going to impact the rest of the system much. So that kind of attack is harder as well. Okay. Number two, the data and application tiers can be scaled separately. Okay, what does that mean? Means, Suppose your organization is managing the same number of clients and the same number of applications, but your data is getting really big. You're getting a lot of extra data. Well, in a client-server model, you'd have to put all that on different machines, right? So every machine where you have the data, you'd have to also include all the applications where people are using it. Here you don't. Here you just have extra data machines. So you can scale out the data tier. Likewise, if you have more applications that you're running, you can scale out that, but if your amount of data is the same, you don't need to add any extra machines there, right? Client-server, if either one changes, you got to increase for both. In Ntier architecture, you don't. So that's a benefit. Number 3, easy to switch between applications and data as needed. Okay? In client-server, you're connected to a particular machine. In Ntier, you're still connected to a particular machine, but the real benefit is this. All of this stuff here, this is behind the organizational boundary. And so the assumption is if a client has logged into an application server and connected there, then he's secure, he's been verified, and he can access any of these data machines through that application server that have data that he's allowed to see. Okay, so switching between these two machines, that can happen very quick because you don't have to jump through all those security hoops. If every time you logged on, right, you had to jump through a new application server, yeah, that would be some extra hoops there. Okay, but in this case, yeah, there's a load balancer as an interface, you know, for this kind of cloud system, for example. That one is going to direct you to a particular application server, and then you're there. Okay, I should add as well, it's not really in the slides, but so I won't test you on it, but quality of service is easier to manage because users are dynamically assigned to servers. Okay, so when somebody logs into the system, basically this kind of system is going to look and say, okay, here's an application server that's running your application, but we also want to put you onto one that's not overloaded. In client server, right, there's just that one machine that's running your applications, you log onto that one, and if there are too many people using it, it's just going to slow down. All right. So that's it. That's generally speaking, Ntier architecture is a lot better for large-scale usage. So, what you'll often see is that different vendors, when they're trying to talk about this model, different vendors will use different language for it. For example, the client tier, some will call it a presentation tier, right, in that this is what's getting presented to the users, or just the user tier, which is obviously the same thing, right? Different words for the same thing. Sometimes you'll see application tier as application logic or server tier, whatever. And data or database tier are pretty typical for that. And again, varies by vendor. Okay. Now, related to this, we'll talk about tight and loose coupling. Okay, so tight and loose coupling means system components are dependent on each other, how dependent they are. So in a tightly coupled system, there's a lot of dependencies built in. One part of the system depends on the other part working in a particular way. Okay? And because of that, you can get some high performance out. You can squeeze out some extra power from the application. In a loosely coupled system, the components are relatively independent. And the benefit there is that it's easy to modify. They don't need to know how all the other parts of the system are set up. Okay, so non-technical example. Suppose I want to tell you about a movie. I just saw some movie and I want to tell you about it. With tight coupling, the assumption would be, I know what you know, right? I know the things, not what you know. I know your level of knowledge. So we both speak the same knowledge. We both, have whatever knowledge of film jargon. We can have a fairly detailed conversation, right? I can specifically talk about film aspects that non-specialists wouldn't know about. Okay, that's tight coupling, and in that sense, it's a high-performance message. With loose coupling, basically you're going to communicate through generic interfaces. In the case of movies, that might be standardized mechanisms like ratings or symbols. So I'd have some preset list of categories like the acting, 5 stars, 1 to 5 stars, the plot, 1 to 5 stars, the costumes, the scenery, whatever, the music, all of that. You could get an idea of whether the film is good or bad, but it's not going to be as detailed as this. Okay? So that's essentially the trade-off. Now, in network systems, right? In a tightly coupled system, all those components are integrated with knowledge of how all the other pieces work. So you knew what kind of hardware was there, you knew what kind of software they were running, you designed communication protocols to be optimized specifically for particular hardware and software communication, right? And it's very efficient, potentially, but if any of those things change, then the whole system has to change. If you start running some new software, or you replace one kind of hardware with another, or you add another machine to the network, it could throw off your whole carefully calibrated system, okay? In a loosely coupled system, on the other hand, communication happens through standard interfaces. And the point of these standard interfaces is you only specify the inputs and outputs. You don't care what application it's coming from, you don't care what hardware is running the application, it's just if the input is in the correct format, you are good. And because of that, this kind of system is very easy to change, but the performance is going to suffer a little bit. Okay, so example, so when you go to a store and you're buying a video game, do they have one version of the game for every operating system? They do not, right? They have a section for Mac and a section for Windows, right? Yeah. So in computer programming, there's a language called Java, which is a universal language, right? If you write the source code is the computer code that humans can understand. If you write the source code in Java, it can run on any machine that's Java capable. Basically, that machine's hardware configuration has been translated, mapped to something called a Java virtual machine, and it'll run on that. But the problem is, because of that universality, it doesn't run very well. You don't want to run cutting-edge video games in Java for that reason, right? You're going to have a little bit of a speed hit. You're probably going to have a little bit of a graphics hit. It's not going to work as well. So games these days, typically programmed in some language like C++, it's basically machine-specific, or at least operating system-specific. So you have one version for Windows, one version for Mac, right? And it's not quite tightly coupled, but it's definitely tighter coupled than an application written in Java. Okay, so the way things are these days, most of these systems, like Ntier architecture, they are designed as loosely coupled systems. And the reason is, changes to the network configuration are far more important to manage than squeezing a little bit of extra performance out of it, right? Computers are powerful enough these days that an extra, 10% or so power in the system, except for the very most cutting edge applications, isn't going to make much difference. But what does matter, if you're something like Facebook and you're adding on, 1,000 hard drives worth of data every day, you have to plan for change. Your system has to allow it, right? Amazon, they're changing their product mix every day, and they're running cloud, and clients are canceling, and clients are coming on. They're changing all that stuff every day. Flexibility is more important than just computing power. Okay, so that's why the trade-off is the way it is. Most systems these days that are big, they have to be loosely coupled. Okay, now an example, well, let's close out the Ntier architecture. So, advantages, it's easier to maintain that system, right? It's more expensive to build, but once you've gotten it in place, it's easier to make modifications. The components are modular, which means they're designed around filling a role. You can have any server, as long as it uses the same interfaces, doesn't really matter what hardware you're using, right? You can swap out one server for another, and it'll probably be fine. The other thing, it's isolated. Changes in one part of the system are not going to directly impact any other part of the system. In a tightly coupled system, yeah, they will. You change one piece of hardware, it could throw off everything. Ntier, it's not going to. In terms of security, it's not a total slam dunk that security in Ntier is better than security in Clientserver. There's pros and cons. But one of the nice things about Ntier is it's easier to test your system, right? So one of the problems with Clientserver is that, you have to design a reasonably representative set of use cases, right? Which can be a little bit difficult to do. Whereas with Ntier, you can say, well, we know that since one component is basically going to work the same as the other, it's pretty easy to do. Clientserver, you have to test every specific configuration possibility, whereas Ntier, not so much. Again, because you test if the interfaces are correct and they're working correctly, then the rest of the system is mostly going to work correctly. Okay, and scalability. Scalability is the big thing. So in Ntier, you can scale the tiers independently. So if you have more data, you can add more machines to store the data. You don't have to add on more application servers. Or if you need to manage more clients in a wider range of applications, you can add more application servers. You don't have to scale out the data tier. Okay. Last thing, I guess, as a kind of a footnote, the fact that your system is already modular, in a sense, it's not that hard to take this system that's already designed to be loosely coupled and modular and port that to a cloud. In that sense, all you're doing, you're taking this system that actually works under your roof the same way, essentially, it's going to work in the cloud. So if you're going to, at some point, migrate to the cloud, you definitely want to have your data set up like this. Okay. At least if you're, too big to be using client server architecture. Okay. Now, customers aren't the only people that use Amazon's processing system, right? There's other, other businesses, for example. They're doing payment verification. They're interacting with Amazon's warehousing operations, for example, if they get a reorder request. And, of course, the shipping services. So their systems have to interface with it to exchange notifications. Well, remember we talked about these kind of loosely coupled systems, they operate through standard interfaces. Well, one example is objects for ordering. So suppose I'm ordering something. Well, Amazon has to communicate to that order what happened to everybody else involved. So it has a standard way of presenting what constitutes an order. So what they do, if somebody places an order, Amazon in some sense is going to create an invoice object. So an object in this sense is like a computer representation of something, right? So we'll make an object that has everything that's in the invoice, and then we'll wrap some metadata around it. Metadata, data about the data. So, concrete example. Suppose Joe Snow places an order, and he gets a red hat, a yellow shirt, blue pants, and a hardcover copy of Green Eggs and Ham, and has it delivered to 456 Igloo Circle. Okay? That's his order. Amazon needs to make an invoice object of that so it can track that in its various databases. All right. Now, there's a lot of different ways you could structure that data. But let's take a fairly natural, human, intuitive way to do it. And we'll separate it into customer, address, item count, and the item. So the customer, the customer is Joe Snow. That's going to be included there. We know the address, right? And we're also going to add, this is in US format. So that's metadata. It's data about the data, right? Because other addressing systems around the world could be different. They are different. We also have another thing, item count of 4. So 4, that's metadata, right? It's data about the data, describes how many things there are, but it's often useful to have that as a separate quantity so I don't have to, scan through and count them all every time I want to check. I can just look up the number. And then the 4 items themselves in some format, right? So clothing may be described with color, book may get a couple attributes, the title and whether it's hard or soft cover. Okay, so I bundle all those together in some fashion, and I make an object. And I have a standard way of saying, this person is buying this, ta-da, and then I can retrieve it whenever I need to, send it, retrieve it. Okay, so there's two main languages for this sort of object modeling. The first one is XML. So, XML, if you've ever seen HTML, the language of web pages, XML looks a lot the same, looks and works a lot the same. Okay? It is in decline, so you don't see it that much, but it is still out there. You might see some XML documents at some point in your business career. So, let me give an example, and then you'll see like, oh yeah, that's why people don't use it. So, here, you have an opening tag for everything and a closing tag with a slash. So the very first one up there, it says invoice. That's the start of the whole invoice. At the end, you have the closing tag for invoice, right? That's where it stops. So for everything that you have, there's an opening tag and a closing tag. So we see at the top right there where it says first name Joe, close out first name. We have 3 characters of data, okay? But to wrap that 3 characters of data, we actually have 23 characters of encoding, right? So 11 characters for first name and the 2 pointy brackets, and 12 characters for slash first name and the pointy brackets. So 23 bytes worth of wrapping paper for 3 bytes of data. It's kind of bulky. It's not very efficient, right? Some people often look at this. They also see it hard to read. But, that depends on how it's laid out. So, annoyances with XML, why it faded from use, relatively bulky, okay, requires conversion, some kind of conversion. If you want to show it on a web page, this is not inherently a web format, right? It's not automatically going to be readable. You need to have some kind of software translation to convert that to something that appears on a web page. Making arrays. An array is a way of counting where the data is stored. So, for example, this list of 4 items, you could construct that as an array, and you could say, well, I want to find the 3rd thing in that list. There's not an automatic way, short of scanning the entire list and counting 1, 2, 3, that's the 3rd thing. With the next object description language, we'll see, in fact, there is. Okay? Last thing, often hard to read, although your mileage may vary, right? Some people think it's unreadable. I guess other people probably have gotten used to it. I don't know, but it's considered harder to read. The alternative is JavaScript object notation, or JSON. So, JSON is a different object description style based on JavaScript. JavaScript will eventually do a little bit of it in this course in the labs, but what it is, it's a scripting language for active content on web pages primarily. Now, we'll take a look at it, and this is the same object, right? This is an invoice, but this thing has all of the data inside. So, customer, right, has this list of things. You'll notice there's no closing tags, right? So, first name, Joe. So, instead of having 23, what do we have? We have 11 and a semicolon, or and a colon. So, 12, it cuts that overhead in about half. And if you don't have a lot of data, but your tag names are fairly long, then that's you're saving about half your data. So, big advantage, it's a lot more compact, right? In typical usage, it might be like a quarter to half as much data gets saved. Which, if we're just talking one document like on, one object like on this slide, you'll be like, well, what's the big deal? But think about if you're sending, hundreds of petabytes of data somewhere, and instead of sending 100 petabytes or storing it, you cut that down to 50. You're saving a lot of money. The other thing, it's going to send it faster, right? So it's not just storage costs, and it's not just the time of searching through all these lists, but if you're sending it over a network, lots of data in JSON format, it's more compact, so it gets sent faster. So everything that happens in your network is going to be faster because of that. The other thing, there's no conversion needed for typical use. So since JSON is based on JavaScript, any browser, and all modern browsers, all the popular ones anyway, they all support JavaScript. You don't need to do any kind of extra translation. If you're running some kind of JavaScript on your page, you can automatically grab that object and you'll know how to display it. Okay, so you don't have to have any other software wrapper around that. Now, JSON's not the only thing out there. Google was trying to come up with a competitor to it. I don't think it gained much traction because even if it was slightly technically superior, nobody wants to take 100 petabytes of data and reformat it all, right? Unless there's like a really good reason to do it. So JSON's still the big one out there, but there's other languages trying to get traction. Okay, so that's the end of that. Now,